Hello and welcome to the Preparatory workshop for the Part 3 Foundations courses. So this video will be on ordinals and cardinals. Hopefully you have seen all of the other videos by now, so I shouldn't have to explain anything. A point that I should make before we start is that everything here again can be carried out formally in the language of theory using first order logic and so on, and it is expressed in this way. But you will see that by now, most of the definitions that we'll be using will be more informal, but this has the benefit of also being more readable and intuitive. Okay, so set, first of all, S is said to be transitive if every element of S is also a subset of S. Okay, how can we express this? By a first order formula, we would say that for all X, and so if S is our set, then the following sentence for formula expresses that S is transitive. For all X and for all Y, if X is in Y and Y is in S, then X is in S. Okay, so this, I think this shows more why we call this property transitivity, because it looks like the binary relation is transitive itself. Okay, a set now is said to be an ordinal or an ordinal number if it is transitive and well ordered by epsilon. Okay, meaning we saw well orders in the previous video. The binary relation epsilon, it defines a total order on S such that every non-empty subset of S has an epsilon minimum element. Okay, now the second part is it will always hold, assuming foundation, the last part always hold. And what do I mean by the last part? I mean the fact that every non-empty subset has an epsilon minimum element. Okay, so under foundation, being an ordinal is simply equivalent to saying that you're transitive and you're totally ordered by epsilon. Okay, so this is expressible by a formula in the language of set theory, and therefore if we write down this formula, we may therefore think and talk about the class of ordinals. Recall that a class is simply a formula with a single free variable. Okay, so a lemma, which I would recommend doing as an exercise, is first of all that the empty set is an ordinal. And often, in fact, when we think of the empty set as an ordinal, we actually write 0 for it, and this will make sense. The second point is that if alpha is an ordinal and beta is an element of alpha, then beta is also an ordinal. Okay. The third point is that if you take two non-equal ordinals, then, and so say alpha and beta, and you know that alpha is a subset of beta, then it follows that alpha is a member of beta. Finally, the fourth point is that if alpha and beta are two ordinals, then either alpha is a subset of beta or beta is a subset of alpha. Okay, so these are very important facts, but they're all actually, they can be shown very easily just from the definitions. Okay, so I would recommend doing this as an exercise. And in fact, I will recommend doing the corollary as an exercise as well, which says the following. So first of all, assuming we've shown the lemma, it is clear that epsilon is a total order on the class of ordinals. Okay, why is that? Well, it is clearly transitive. Secondly, it is irreflexive, of course, by foundation, and it is antisymmetric because of points 3 and 4. Okay, and in fact, because this is a total order, often, and that's the point I'm making with the green letters, often, in fact, instead of writing epsilon when we refer to ordinals, we will actually write alpha is less than beta with a standard less than symbol to mean that alpha is in beta. Okay, so this is just notation. The second corollary to the above is that if you take a non-empty class of ordinals, then the intersection of all ordinals in this class is, well, the intersection of this class is an ordinal. Okay, the intersection of this class is in fact a member of this class, and that the intersection is in fact the infimum of the class under this order, this epsilon order. Secondly, if you take a set of ordinals now, which is non-empty, then maybe you should say, I'll just write it this way. Then the union is also an ordinal. Okay, that's good. And in fact, the union is the supremum of this set. Of course, the supremum in what order? In the order defined by epsilon. And the last consequence is that for all ordinals alpha, the set alpha plus, which is defined again, if you remember from the infinity axiom, it's defined as alpha union the singleton alpha. It is an ordinal, that's an easy consequence. And not only is it an ordinal, but in fact, it is the infimum of the class of all ordinals that are above alpha. So in fact, what this means is that alpha plus is the successor of alpha in this order. Okay, so this order, amongst other things, it is discrete. Okay. Now, a very important theorem, which is provable in ZF, is that if you take any well-ordered set, then this is order isomorphic to a unique ordinal number. And what do I mean by that? That there is a bijection going from our set X to alpha, such that for any two elements of X, it holds that S is less than T in the order of X, if and only if f of S is in f of T. Okay. So this has several important consequences, which we will be seeing a bit further down. But yes, this was shown in the Part 2 Logic and Set Theory course. You can find a proof of this basically anywhere on the internet, but if you want, you can even find this in the notes from last year. And yes. Okay. So the last point, and the fact that this order is discrete, allows us to make the following definition. So we say that an ordinal alpha is a successor ordinal if there exists an ordinal beta such that alpha is the successor of beta in this order. So if alpha is not a successor, then it holds, in fact, that alpha itself is the supremum of all things below it, okay? In which case we say that alpha is a limit ordinal. We will also consider 0 to be a limit ordinal, and the supremum of 0, or the supremum of the empty set, is simply 0 itself. Okay. So we know that there are successor ordinals, and in fact, we know that there are limit ordinals as well, non-zero limit ordinals, and this is precisely what we obtained through the infinity axiom. Okay, so the infinity axiom simply gives us an inductive set, but we can make sure that this inductive set is an ordinal itself by possibly using separation if we have to. Okay, so limit ordinals exist, non-zero limit ordinals, in ZF, and we denote the least non-zero limit ordinal in the class of ordinals as we write omega for this. And all ordinals which are in omega are called finite ordinals. Two very important theorems that should be in your set theoretic arsenal are the following. So the first is transfinite induction. So transfinite induction says the following. Suppose that we have a class of ordinals C that satisfies the following. First of all, 0 is in the class. Secondly, for any ordinal alpha in the class, the successor of alpha is also in the class. And thirdly, for any non-zero limit ordinal, if we know that all members of this ordinal are in our class, then we also know that this ordinal is in the class. Assuming that I have a class satisfying this property, then it must be that the class is the class of all ordinals. Okay. So this is a very important theorem, especially for proofs, and for proofs of, for showing properties of things that have been defined by recursion. Now, what is recursion? I will not give you the full statement of transfinite recursion here. What I will do is that I'll give you a weaker version of it, and in fact, I'll even give it informally. For the formal statement, I would recommend looking at Thomas Yeck's book. There's a chapter on ordinals. And in fact, even in the Part 2 Logic and Set Theory course, the formal statement was not explicitly proved ever in the course. So nonetheless, I'll give you the one that is the most useful, I think, for most arguments you'll have to do. So what it says is the following. If G is a class function on the class of all sets U, then we may define a unique class function f on the class of ordinals via transfinite recursion. What does that mean? We say we can define, we start at 0, so f of 0 will just be G of 0, where G is this fixed class. Now f of alpha plus will be G applied to f of alpha for all ordinals alpha. And finally, for limit ordinals lambda, f of lambda will just be the union of the set containing f of beta, where beta is in lambda. Okay, so assuming that G is a class function in U, then we may define a unique class function on the class of ordinals in this particular way. So with this, we can actually make several very intuitive and important definitions by recursion. So for instance, we may define addition on ordinals. So this is defined in the following way. So for any ordinal alpha, we define, first of all, alpha plus 0 to be alpha. Secondly, alpha plus the successor of an ordinal beta to be the successor of alpha plus beta. And finally, alpha plus lambda, where lambda is limit, to be the union of the set alpha plus beta, where beta is in lambda. Recall, by the way, because of the corollary that I talked about before, that the last sort of set, this one, and in fact, I mean this one, oops, sorry, no, I just meant that one. This is going to be an ordinal. Why is that? Why is that? Well, alpha plus beta by induction are all ordinals. This is a set of ordinals. Why is it a set of ordinals? Lambda is a set. By replacement, this is also a set that exists. And therefore, the union of this is an ordinal. Okay, and in fact, the supremum of all of these things. Likewise, we may define multiplication of ordinals. So this is again defined by recursion. So for any ordinal alpha, we say that alpha times 0 is 0. Alpha times the successor of beta is alpha times beta plus alpha, where beta is any ordinal whatsoever. And finally, alpha times lambda, where lambda is a limit ordinal, is simply the union or the supremum of the set containing alpha times beta, where beta is in lambda. Okay, so these are well-defined definitions of ordinal addition and multiplication precisely because of transfinite recursion. As an exercise, I give to you the following. So show by induction that both ordinal addition and ordinal multiplication are associative. Okay, so you'll have to think where exactly you need to induct on, but in fact you will realize very quickly that because the recursion occurs in the second argument of both addition and multiplication, you need to do the induction argument. Again, you will show this by induction in the second argument. Okay, let us move on to cardinals. Now, an ordinal number, kappa, is called a cardinal if there is no element of it, no alpha in kappa, and a bijection from alpha to kappa. So clearly this is definable by a formula in the language of set theory. So this formula defines precisely the class of cardinals. Now, by the theorem I gave to you before, that says that every well-ordered set is isomorphic to a unique ordinal, and the axiom of choice that tells us that, or the well-ordering principle, if you like it, that says that every set must be well-ordered, it follows in ZFC that every set is in bijection with some ordinal. Therefore, we may define the cardinality of a set to be the infimum, so the least ordinal, which is in bijection to this set. Okay? Clearly there is such an ordinal. We simply take the least such one. And we know that this is an ordinal. Why? It's the infimum over a class of ordinals. It's by the lemma, by the corollary, that I mentioned before. This is an ordinal. Okay. So, the following lemma, I would recommend doing it as an exercise. But in any case, it says the following. So for any two sets x and y, first of all, the cardinality of a set is not only an ordinal number, but in fact it's a cardinal number. So this is almost a tautological statement. Why is that? Well, we define the cardinality to be the least ordinal, which is in bijection to our set. Well, if the cardinality was not a cardinal, then there would exist some ordinal which was in the cardinality of the set, which was in bijection to it. But this ordinal, because it is in the cardinality, it is smaller than the cardinality, and therefore the cardinality is not the least, and because bijections compose, and they still give bijections, the cardinality would then not be the least ordinal which is in bijection to our set, which is a contradiction. Therefore, the cardinality has to be a cardinal number. Okay, secondly, it's not difficult at all to observe that two sets have the same cardinality if and only if there exists a bijection between them. Okay, that's easy to show. Thirdly, the cardinality of a finite ordinal is itself. So the cardinality of n is n. And so in particular, every finite ordinal is also a cardinal. The fourth point is that any cardinal which is not finite, so every infinite cardinal, is a limit ordinal. So this is easy to show. And why is that? Because the successor, if alpha is an ordinal, the successor of alpha is in bijection to alpha. That's easy to show, and that is precisely for infinite ordinals. Okay, and that would mean that cardinals could not be successor ordinals, they would have to be limit ordinals. The last point in this lemma says that if X is a set of cardinals, then the supremum of this set will not only be an ordinal, but in fact it will be a cardinal. All of these are not difficult to show. I kind of sketched the argument for some of these. I think they're fairly straightforward. Now, what else can we say about cardinality? Well, it is a famous theorem of ZF, which was shown by Cantor, Schroeder, and Bernstein, that if x and y are two sets such that there's an injection from x to y and an injection from y to x, then there's a bijection from x to y. Okay? And what does that imply? Well, consequently, it follows that the cardinality of a set is less than or equal in the ordinal order than the cardinality of a set y if and only if there's an injection from x to y. Okay? The next point, which is also very important, and it was shown by Cantor, is that for every set x, the cardinality of x is strictly less than the cardinality of its power set. And so this means in particular that for any set and for any cardinal, there exists a bigger cardinal. Okay, so much like before we defined addition and multiplication of ordinals, we also define addition and multiplication for cardinals. But this time, we do not have any kind of cardinal induction or recursion, okay, because these are not kind of built in steps like ordinals are. But nonetheless, we can define them in this way. So given two cardinals, kappa and lambda, The cardinal kappa plus lambda is the cardinality of the set kappa union lambda. Okay. And in fact, actually, I shouldn't say the cardinality of the set union. I should say the cardinality of the set kappa disjoint union lambda. Okay, this is now correct. How do we define product? So kappa times lambda is the cardinality of the set of the Cartesian product of kappa and lambda. Okay, and finally, the cardinal kappa to the power of lambda is simply the cardinality of the set of functions from lambda to kappa. Okay, so it turns out that this notion of addition and multiplication and exponentiation in fact behaves very well not only for cardinals but for any sets. And this is precisely the content of this lemma, which again I would recommend doing. It's an exercise. It says that for any two sets x and y, the cardinality of x plus the cardinality of y is equal to the cardinality of x disjoint union, sorry, that should say not just union, y. Secondly, the cardinality of x times the cardinality of y is simply the cardinality of x Cartesian product y. Now notice that these are not tautological, it doesn't follow by definitions. Why is that? Because technically what the definition would tell us would simply be that the cardinality of x plus the cardinality of y is equal to the cardinality of x union the cardinality of y. So what the lemma tells us, for instance, for the first point, is that this is equal simply to the cardinality of x disjoint union y. Okay. The third point is the same kind of point for exponentiation. So the cardinality of x to the power cardinality of y is simply the cardinality of the set of functions from y to x. And finally, the cardinality of the power set is equal to the cardinal 2 to the power of the cardinality of x. Okay, so finally, a last point that I need to make here, which is important and will be very important in the large cardinals course, is that given a cardinal, we know by Cantor's theorem that there exists a cardinal which is bigger than a cardinal, so we may define successor cardinal, which we denote by kappa plus. Notice that the notation is a bit, it depends on the context. If we treated kappa as an ordinal, then kappa plus would simply mean the successor ordinal. Here, we're sort of thinking about cardinals, and so by kappa plus, we mean the successor cardinal. And this is simply the least cardinal that is above kappa. And there is such a cardinal by Cantor's theorem, we can simply take the least such one. Okay, and therefore we can define by recursion this sort of aleph hierarchy. Okay, how do we define this? So by recursion, aleph 0 is simply omega. So omega is, recall, the least non-zero limit ordinal. It's an easy exercise that this is a cardinal, right? Aleph of alpha plus 1, where alpha is an ordinal, is simply the cardinal successor of aleph alpha. And finally, aleph lambda is simply the supremum of aleph beta, where beta is, this should say, less than lambda, for lambda limit. Okay. Any set whose cardinality is aleph 0, so that is omega, we say that it is countable. If a set is not finite nor countable, we say that it is uncountable. And cardinals of the form aleph alpha plus 1 are called successor cardinals, and on the other hand, cardinals of the form aleph lambda, where lambda is a limit, are called limitor.